Today we're going to be taking a look at this 2020 M1 MacBook Air that does not turn on after a liquid spill with a previous repair attempt. So that's where it gets a little bit tricky. So there's flux all over this board. Let's go ahead and plug it in. Let's see what it does, as always. So we have our USB-C charger with our USB amp meter, and I see one port's a little bit corroded, so I'm going to kind of avoid that. And we're plugging into the other one, and so far I have 5 volts and 0.01 amps. Now, 5 volts, 0.01 amps could mean many things. One of the things in our differential would be a short on PP bus G3 hot. That's pretty much unchanged from all of the T2 MacBooks all the way up to the M1 Pro and Max machines. Is if there's a short on PP bus G3 hot, it will present as 5 volts and 0.0, 0.01, 0.02 around there. But anyway, it had a previous attempt, so let's go ahead and look at this first and see what's going on. So I'm going to switch over to my microscope view, and let's have a look. So, looking at it on this side, I see liquid got on our NAND, which is not a concern actually because our NAND is underfilled. What is a concern is if any of the NAND power circuitry got affected. Now this is our 3V8 AON circuit. 3V8 AON is basically the VCC main of these M1 MacBooks, and this powers many things. So we actually have 3 phases. This powers the CPU PMICs, so it does need quite a lot of current, so that's why we have 3 phases here. So I have a little bit by my trackpad connector, not going to cause 5 volts, 0.01 most likely. Carrying on. Alright, and this, okay, this definitely had touch-ups. And what is this? Okay, first contender is this. This does not look very good. So I don't know what this does. We're gonna find out, but this does not look very good. And I'm gonna guess this looks like an inductor here. So this may very well be 3v3 G3 hot. That is not soldered properly. You could see there's balls shooting out. There's missing components. There's a capacitor that's just chilling out over here. So this is definitely one of our top contenders of what's wrong here. Carrying on, we have our ISL 9240, which looks like it's been replaced as well. There's a chip in the corner of this chip right here. So there's a chip in the chip. That's no good. This top layer here is actually silicon. Well, the whole chip is silicon, I should say that. But the top layer, there's no components in the top layer of this chip. It's all on the very bottom layer, and it's a very thin layer. So if we get a chip in the top of this, it's probably not going to affect anything. But that's noted. Let's carry on. Up here, here's our CD3217s. These have been worked on, looks like. There was something here, either probe points, or there might have been a BGA here. I can't tell, but that one was ripped off, or just the probe points were degraded from cleaning. Doesn't look like these guys were corroded because all the components around them look okay. There's no signs of liquid around this. When we look at something like, let's say this ISL, we can see that there's liquid here. There's a capacitor here that looks funny. These resistors have kind of a atypical appearance. I don't like the way those look right there. Those might be blown, but I do not like the appearance of these guys right here. And you could just tell there was liquid. Same with around here, okay? Capacitor, gray end, liquid, previous liquid. So there's definitely a problem here. So how I'm going to approach this, since it is a previous attempt, I am going to take a look at I'm going to fix the worst looking thing first, and that's going to be this. So I need to figure out what this does, and does it correlate with our problem. So let me go ahead and open a board view for an 820 2016 board. This board view is available courtesy of WizKid from Bad Cabs Forum, who actually manually made this board view. He's working on a 820-2100 board view as well for the 16-inch MacBook Pro, and he has a GoFundMe, or not a GoFundMe, a Kickstarter for that board, because he actually has to purchase a 16-inch MacBook Pro to finalize it. So I'll be posting that link shortly as well to help him out. Okay, let's take a look at this board view. You can see the quality of this board view. It looks just like an Apple board view, and this was pretty much 100% made by hand by WizKid. So definitely really, really nice work. So looks like our area that was corroded was this. Now, PP bus, AON, IPD, something or other. So IPD typically stands for trackpad, okay, but it does have PP bus going in here, so maybe this is shorted. I don't know, but either way, this has got to go. It looks like we had a capacitor here on PP bus that looked ugly, and this one missing was on PP bus AON SW IPD underscore DVD T. Now I don't know what any of that means, but I do know this is probably a derivative of PP bus G3 hot. So I am going to probably, next step is I'm going to rework this, but before I do that, I want to check for a short on PPBus G3 hot. So it looks like this is our PPBus AON fuse right here, so I'm going to go over here, and let's check for a short and see if that's shorted and see if we have voltage there, because 5 volts 0.0 typically means that our 3.3 volt rail that powers our CD3217s is not powered either from a short on PPBus or from PP bus being missing, and our ISL 9240 right here is what generates PP bus, had previous rework, has a chip in it, so that's definitely a contender right there. So I'm going to plug it in. I'm going to find our fuse. Where's our fuse here? Here it is, marked by W. Kind of hard to miss. We are going to plug this in. And let's measure what PP bus is. It should be around 12.3 to 12.6 volts. And I'm getting 0.0 volts on this. Let's check for a short now. Unplug this. And I do not have a short. Okay, so as of right now, my leading contender is going to be either one of the CD3215s that's not passing PP bus through, or our ISL with a chip in it. Now, I can't trust a chip that's been previously reworked. That's just our policy here. We don't, if anything's been previously reworked, we take care of it because we don't know if we can trust that component. So first things first, let's rework this area. This looks like garbage right here. This does not look good. I don't trust this. So let's go ahead and take care of this. So I'm going to put flux here. It looks like what happened, I don't know if this was replaced. It might have been reflown, and it might have just got knocked around, which happens sometimes. It's something we all can do. Might have a bridge under it, I don't know, but I don't like the appearance of how that chip is sitting, so it's best to get rid of it. I probably could just resolder it, but I don't really trust resoldered chips because I don't know if it previously had a bridge. I don't know how much heat exposure it had prior, so it's best just to get rid of it and move on. Yeah, you could see it looks like it wasn't soldered on those pins right there. So, but that's not going to cause a no power issue. This is mainly going to cause a no trackpad issue. There's that. Let's go ahead and get our solder wick. That looks like it's leaded solder there, so it might have been reworked. I can't tell for sure, but it seems like the melting temperature was fairly low there. Could just be because this board's a little bit thinner as well. And this tip is way too big for my application, so we're going to switch it. That's one thing I see with students too, is they will use the wrong size tip for what they're actively doing. You don't want to use a tip that's too small, and you don't want to use a tip that's too big also. If you use a tip that's too big, you can knock components around that are around it. You know, you'll grab one of these capacitors, fling it off the board, and if you use a tip too small, you can rip pads because it won't actively heat soak the board. The tip that I find is really the sweet spot is the Hakko BC15 or BC50. They're both the same. I think one is a little bit newer than the other. Nope, this is actually lead-free solder. So you see how I'm wicking it? It just didn't want to be cleanly sucked up into the wick. That is lead-free. So what I'm going to do is put a little bit of leaded down. A little bit more flux in there. Anytime you see your joints doing that, just add more flux. This is going to get ultrasonically cleaned anyway, so we don't have to worry about making a mess. And flux makes everything prettier. A little bit of oxidation on these pads, probably from heat. Really minor. Again, I'm not worried about a blob. I'm just trying to clean up all that lead free. And now I'm going to wick it away. I know you guys have some glare here from the flux, but that's not something I could really help. Just like that. Trim my wick. I don't like the looks of this resistor either. See how the coating is like stripped off of it? There's a white spot. That can be indicative of a resistor that is blown. So anytime something looks like that, replace it. And that's sufficiently wicked. Now I can get fresh solder in here. So like that, like that. You got knocked over, so I'll fix you. Fresh solder on these guys. And I'll make the ends of this capacitor look pretty. And this inductor here. Little bridge there, so I want to take care of that. And it's gone. Alright, now I'm going to fix my resistor that knocked over, and I'm going to take off the other one, and then I'm going to grab a donor board. Just like that. Just like that. And you see that little solder blob that kind of just spread out? That's absolutely perfect, because that should be a sufficient amount on our thermal pad right there. So more flux, and it's donor time. Let me grab an M1 donor board here. I will say this, the M1 MacBook Air is actually a really nicely built machine. Out of most of the machines that we've seen with liquid damage, very few of them have board damage. It's mainly I/O board damage, things like that. Okay, so we have a resistor, a couple capacitors. Okay, a couple resistors and a capacitor, I should say. So first things first, let me replace the resistor we just took off. Actually, that one's a little bit hard to get to. I'll leave that till after our chip is on. There's that one. This guy at the top, and he blew away, so we'll come back for him. Actually, we didn't even need to replace this guy. I totally forgot. In my mind, I thought this resistor was gone, but it's not. It's still there. Let's go for our IC now. Just going to tack it down, get some flux, and let the flux do the work. I want to push down on this a little bit, actually. There's that. Now I could just clean up the little blobs on the side with my iron. there, and that looks good. Let's go ahead and hunt down that resistor on the top that we knocked off. So I'm going to go to my board view. And looks like this is an enable resistor. It's probably going to be a 10K. Let's see. Oh, my lucky day, it's a 0 ohm. So we technically could just run a wire across that, but we're going to be professional and put a 0 ohm 201 resistor back on. I do not condone running a wire across the 0 ohm resistor, and the reason why is the wattage rating. The wire will be able to handle a little bit more wattage, and a lot of times these 0 ohm resistors are actually used as fuses, so the wire may not blow in the same rate the resistor would blow. So I do not recommend you substitute a wire for a 0 ohm resistor in any reason, even if it works. So people will say and argue, well, it works. Yeah, but it won't do what it's intended to do, which is act like a fuse, which is typically why we use 0 ohm resistors. There's that. And I just noticed something out of the corner of my eye, and that is we see some visible pad there on that resistor. So I want to just hold my iron on this just to make sure it's soldered. We're a little bit dry there in solder, so I'm going to add a little bit. A little bit there, and I'll flow this into place now. A little bit more flux. By a little bit of flux, I mean a lot of bit of flux. There, perfect. And moving on. So what strikes me the most about this is not the fact that there was rework. It's these resistors right here. Look at how these guys both look. They both have this same weird striped appearance down the center, and what I think that is, I believe that's the filament in there that got really hot from handling a lot of current. And let's see, okay, see, this is what it's supposed to look like, and this is what this looks like. That doesn't look right to me. So I want to figure out what these guys do and figure out how this happened, because resistors don't just blow for a reason. I mean, a resistor never just opens for no reason. So it typically has a root cause. So let's go over on our schematic here, and we can see here, just open this back up, go back to my display capture. Alright, so R7040 and R7030, so it's going to be this guy and this guy, charger boot 1 and charger boot 2. Let's go this down, boot 1 and boot 2. So these usually refer to bootstrap, and if we go up, see these pertain to the MOSFETs right here. So we have either one of two things happened. Either one of our MOSFETs failed, or we had a really high load on one time under PP bus, which is possible from our battery or from our charger, or something in common blew between these. So if I had this MOSFET that blew, for example, I would expect this resistor to be blown. If this one was blown, I would expect this resistor to be blown. Now both of these are blown, so I am going to point at the thing that's central here, which is this ISL 9240 U5200. Now appearance isn't everything, and for all I know, that MOSFET is going to be totally, that resistor is going to be totally fine. So let's just measure it and let's see. I'm really not sure here, because the resistor might have gotten hot without actually have blown. I can't speak today. So that's a possibility, but either or, I would not trust those resistors, and I definitely wouldn't trust that chip. This chip in the chip, if you will, is concerning. So that looks like it got knocked off maybe. All right. So yeah, these resistors are actually fine, but again, I think the filament just got really hot from handling a high current at one point in time, so that's no good. So I'm going to replace those guys and the ISL 9240 here. Get you out of here. Get you out of here. Get you out of here. Okay, look at this. I think my prediction was right. Look at all that crap under there. That is corrosion. That is previous corrosion that the flux kind of just ate up and is just sitting under there. So what probably happened here is this chip was pulling a lot of power and made those resistors get hot. And this is probably why PP-Bus G3 Hot is not being produced. As you can see here, if we go to the schematic, this chip right here, the ISL9240, actually outputs PP-Bus AON. So look, it drives this MOSFET here, alright, PP-Bus AON right here. So that could definitely explain why this board is not turning on. So let's go ahead and go back to our microscope and let's clean this up and prepare for soldering of a new chip. So I'm just going to get my iron and clean up these solder balls here. These are lead free, so this chip was not replaced prior. Might have just been fluxed and heated, which is fine. I do that too. But if it's severely corroded, it's always best to replace. And look at that. It's just like eating up. I mean, it's just, you could see that all the corrosion in the flux. Can't even see the iron tip under there, buried under it. So let's clean this up. More flux. And the pads are intact, which is good. But look at all that floating in there. There's definitely a lot of garbage under that. This capacitor just has really minor surface oxidation. He'll be just fine, as long as I can get that off and reinforce that joint. So a bridge is normally bad, but this bridge here is perfect because it just kind of enveloped the end of that capacitor in solder. And now I can clear this out. A little bit of wick in a second here when I go through wick. Little bridge here too. We'll take care of that, but I just want to clean up all of this because there's a lot of junk suspended in this flux. Let's clean this up. A little acetone. And now I'm going to go ahead and wick this area. First off, I want to get rid of these bridges here. There's that. And let's look at this. Can't really tell if this capacitor is soldered well or not. I'll reassess after the chip is on and that flux is burned off because it's hard to tell. Looks like that solder joint might be corroded. There. That's beautiful. Now let's trim our wick back a little bit. Let's get this chip on. Anytime you see your iron kind of struggling, raise your temperature. So I'm up at 740 right now. We just want to take our time and make sure these pads are pristine. I'm not applying pressure here. If you apply pressure, you can really give yourself a really bad day. And anytime I see my wick start to get filled with solder, I'm going to clip it back because that excess solder kind of acts as a heat sink. If there's a little bit of solder left on these pads, that's totally fine. We just want to make sure they're flat. And that pad came off right there, a couple pads. And I'm going to guess these are NCs, because NCs are just held on by adhesive. And when you heat soak the area, they can really easily come off. And if we look at our board view here, could see that these are both NCs here, so I don't care about either of those. Now, if you look at this closely, you're looking, well, no, Tim, you're wrong. These are not NCs, and actually they are. So, okay, it has a net, all right, but it's not connected. Okay, if we look at our board view, our schematic here, what is that pin? Let's just do this. Nope, it's not even found on the schematic, so yeah. Not a concern. NCs are something that I don't personally care about them. Some people are really prestigious about them. And it's like, well, you ripped a pad. It's an NC. It doesn't matter. It's still a pad. I don't care about that. I don't operate on that motto. It's literally just a dummy pad held on by a little bit of adhesive. And personally, I don't care if they're ripped off. It's not ripped off. It just came off. In my opinion, it's not unprofessional to leave NC pads off. They serve absolutely no purpose, and you don't need to worry about them. Let's clean this off really well, and we're pretty much ready for soldering the new chip. I'm going to replace my resistors first, though, so I clean this up a bit. That's pretty clean. Let's get a little bit of flux here. Let's get these two resistors replaced. And there's that. So let's go ahead and get our new chip now. It's a BGA, so I'm only going to use a very small amount of flux, because BGAs like to run away if you use too much flux. So I'm going to grab an ISL 9240 from my stash. And our orientation is the dot is in the top left. So we got to remember that. Don't put your chip on the wrong way. Bad things will happen if you put this chip on the wrong way. And the chip just flew out at me. Now, normally we wouldn't care about this, but this chip is precious. So I'll have to track down that. And it's probably gone in the abyss. So we'll grab another one. I literally saw the chip flinging towards my eye. Let's go ahead and get him aligned there. No, come back. That should be good. Let's go ahead and get this chip on the board now. And I see it's a little bit off, so I'm going to nudge it. You could see this capacitor at the top better now, and it is totally fine. So We're just going to leave it be. I see my chip moved a little bit. So I'm going to up my airflow. And it is fully in place now. Let's let it cool, and then let's give it a test. These CDs here, I'm just going to heat these guys up a bit. I don't think these are bad, to be honest. So we're just going to let that be. And then let's see, while it's cooling, I'm going to look on my board view if there was anything at the top of this, and it's not. These are just test points, so there was no BGA in this area. Let's let it cool, and hopefully we get a working board. So this board should be 21 milliamps. I mean, not 21, 20 volts, and some really low milliamps because this processor is super power efficient. So let's let it cool about 30 seconds, and we'll test it. All right, let's plug this in and let's see if it works. So on the USB amp meter, before we had 5 volts and 0.01, and now we have 20 volts and 0.12, 0.7, 0.8. Now this is a really power efficient processor, and I believe it's going to it's going to chill here for a minute, and then it's going to go up from here. Let's see what it does. Now another thing is this processor is really power efficient, so for all we know, it's actually booting right now. There we go, 0.19, 0.7, 0.30. Okay, now we're definitely in the booting range. 0.20, 0.12. See, this could be booting right now. Like I said, these things are wicked power efficient, and they're not like the Intels that'll go up to like 56 or so. So this is probably booting. 0.24, 0.16. Let's go ahead and actually test this in the enclosure, and let's see if we fixed it. Alright, so overall I just looked at the enclosure. We have a few areas of minor liquid. Our audio board has a little bit of corrosion, so that'll be ultrasonically cleaned. It's unplugged for the time being, but I don't really care about that for now because that's not the board, not what I was fixing at the moment, so we'll handle that out of the video. But I want to see if this boots. So 20 volts, 0.45, 1 amp. It is charging the battery, and we're going to hope for an Apple logo here. 2.18. No trackpad click. Okay. 2.32. So the 2 amps is the battery charging typically. And our heatsink is warm. So this raises my suspicion that something else is not quite right here. So let's go ahead and unplug this. Let's unplug our battery and let's get a baseline amp draw reading. Oh, I guess in order for a board to have image, you have to plug in the screen, don't we? And if we look at this, our screen is actually unplugged underneath the board. So that would definitely cause a no image issue, and you can see Caleb here laughing at me because you could see my true intelligence off camera. That's when it's just comical when I see people comment, "You're a genius" and stuff in comments, and it's left the freaking screen unplugged, and I'm wondering why it's not working. So our trackpad cable is a little bit corroded, so that's probably why we didn't have trackpad click there, and there was one pin on the trackpad that looked a little gnarly. So we'll swing back around, but I want to see if I have image here. So let's plug this back in. Okay, so now we have the screen connected, and we still have no image. So this is more kind of acting like the CPU isn't getting power. So let's go ahead and pull our heatsink off, and let's have a look and see how our PMICs look. It could also be in recovery mode here, but we really don't know what's going on at this point until we get our heatsink off. So let's actually just do another little overview because we want to make sure we did not miss anything. And let's just look. Okay, we have some corrosion right there. Here's our screen connector. Looks fine. This is where previous attempts honestly really suck because we don't know 100% what was done prior. And another possibility is all this flux everywhere is causing an issue. Alright, look at that. Coffee or whatever this was definitely got under here. So let's take this heatsink off. It's acting like what if I were to take a guess of what's causing a problem now, it's acting like possibly one of the PMICs for the CPU is not working right or is corroded. Okay, our heatsink is off. And these guys look totally fine. So does our CPU. Nothing got under here. This is totally clean. So what I'm thinking right now, this board, we don't know the history on it. We know it probably had liquid damage. It has a ton of flux on it. So what I'm going to do is I'm going to ultrasonically clean this and see what happens. Another possibility here is let's see if we have 3V8 AON. Because 3V8 AON does power a lot of system function. I don't know if we would get 20 volts if 3V8 AON wasn't working. But let's just check it. Rather be safe than sorry. But I kind of feel like this is one of those ultrasonic cases where ultrasonic will end up fixing it. Just because of stuff being corroded. 3V8 AON. Oh, okay. 3.7 volts. And our CPU is cold at the moment. 3.7. 3.7. Okay. Now let's see what our CPU does. Alright, so our CPU does get a little bit warm when it spikes upward. So that is concerning. For sure. That is definitely concerning. But I don't see a method. I don't see a method where our CPU could have got damaged in this way, unless this little bit of corrosion there. It's hard to say here. So, what's this? What was this here? This looked like a resistor, and it looks like it was knocked off. So this is why previous attempts suck so bad, is stuff like this. You weren't the first one to work on it. You don't know what the other person 100% did. So let's look at what this was. Looks like, okay, R3824, 1V8 AON MPMU, PMU on off L. Okay. This could definitely be something to do with this. Is it a no stuff? No, this is a stuffed pad, so this could definitely be our issue right here. Yeah, this is dead. This is seriously important here. So look at this. Here's our donor, present resistor, not present resistor. So this could be 100% our issue because that's basically our signal for the device to turn on. So it could be trying to turn on. It'll initially power up since the M1 is more than just a CPU. It does pretty much everything that the T2 did and more. It could be doing some other functions first, gets a little bit warm, and the PMU on-off L is just telling it to go in a SO state, basically. It's called something else now. But let's go ahead and get this on here. I'm pretty sure this is going to be it. I could totally be wrong, but we definitely see we have a break in the connection here. We have our via. So I'm going to get my X-Acto knife, and I'm going to scrape away. I don't necessarily need, I just need one end to be right here. So I'm just going to cut away a little bit at this trace. I want to make sure it's fully patent, so I guess I could just scrape all of it. Yep, it's good. And then this little via, which goes to the PMU. I'm going to try and anchor the resistor there. I'm still going to have to run wires, but I want a little anchor there. let's get our resistor. I think this is going to be the fault, but we'll see. And now let's run a jumper. There's one side. That's good. And then on the other side now. And what I'm going to do, I want to see if the amp draw changes. That's going to be my main prognostic factor there. Because remember how it was kind of cycling and wasn't staying steady? Come on. There we go. And now we're going to do a little jumper on this little via over to that resistor. Again, apologize for the glare, but I need flux in this situation, and flux is more important than you guys seeing in 100% clarity. Because if we don't use flux, it looks like you gave a kindergartner a soldering iron and let them add a MacBook, and we don't want that. There, it's tacked down. It's not ready. It's not, by all means, this is not good soldering. So we are going to fix this. We are going to wrap this around like this. Good joint on the resistor. And good joint on the via. That is done. Going to be really careful on clipping this out. And we're going to have to touch that up again. It's all right. Yep. There's one. And there's two. Okay, now our moment of truth. Let's see if our power draw changed. And if the CPU gets consistently hot, that would be my indicator that we probably did something good. This copper wire, 20 volts, 0.08, 0.03, 0.04. Give it a minute, 0.06. And our processor is actually burning hot now. So it's at 0.12 and our processor is very, very hot, which it wasn't before. And this could be booting. Like I said, 100 milliamps, these things are pretty efficient. So that's, I mean, our processor is very hot. So that's kind of concerning, but at the same time reassuring. Because, I mean, these things are power efficient. These chips are very, very power efficient. Remember the first one I got, I plugged in, and I'm like, this isn't turning on. It won't turn on without the screen or without being in the enclosure, and it actually was turning on, and it was like 0.4, 0.14 or something. So very power efficient devices. And let's go ahead and throw this back in here. We don't need a real heatsink on this. I mean, it's in an iPad with no heatsink, so spare me YouTube comments. We're not killing the processor by leaving the heatsink off. Even Intel's we won't kill by leaving the heatsink off. And our screen came unplugged from the bottom of our board again. That is no good. And we did not get trackpad click before, so that's something we're going to take in consideration here. Alright, so it does turn on now. You'll have to take my word. We get an image, but we have no backlight. And it's really not hard to not know why we have no backlight when we look at the screen. So let's have a look here. So we're going to fix this, by the way. But look at this. Look at this. This is amazing. Not really amazing. It's actually sad because I have to fix this. But yeah. That's why we have no backlight on our screen. So let's go ahead and clean this up. Can we get away with just a cleaning? Probably not, because this looks burned. Definitely burned, but I don't know if it's just burned or so badly corroded. It's really hard to tell. No, that's burned. Hopefully the PCB isn't damaged. That's what I can hope for. So we are going to get this screen pulled off, and we're going to get this connector changed. So let's go ahead and pull this screen off and go from there. This shouldn't be too bad to fix, honestly. All right, so our display was actually worse than I thought. Actually had to end up going ahead and splicing a whole new backlight flex cable in here. So what I did is I cut the cable at the base of the screen just like we do on FlexGates, and then spliced a new cable in. So the Airs don't have the FlexGate issue, but it's the same pinout, same basic functionality. So that's done. The display should be fixed. Connector has been replaced as well. So that's all stuff we did off camera because you guys don't really want to see a flex cable replacement. But anyway, let's go ahead and have a look at our board. Now this board has been ultrasonically cleaned, so remember how it looked before. It was full of flux, kind of corroded, looked really nasty. Let's take a look at what it looks like after a 1 minute per side bath in the Crest ultrasonic cleaner. Now you may ask, why 1 minute? I thought you recommended 3 minutes. We revised our standards on the M1 boards because of the processor. Now the processor on an M1 board has a heat spreader. This is a M1 with the heat spreader removed. And there's thermal paste under here, okay, from the processor die to the heat spreader. So if you ultrasonic it for too long, it will degrade this thermal paste and your thermal performance will suffer. So 1 minute aside is perfectly safe, and with a good ultrasonic cleaner, you can see it does just excellent. Remember this pin? All right, look at it now. It looks fine. Let's look at this side of the board. Okay, here, this area was full of flux. This is where we reworked. It looks beautiful now. ISL area, remember how this looked? Looks fine now. Okay, looks pretty much untouched. Carrying on, CD3215 area, looks good. No residual corrosion. Everything looks good. This little spot right here that was like that when I got it, these are just test points. I don't worry too much about these. Everything looks soldered, so it's not a worry. So now let's go ahead and see if this actually works in our enclosure, because this device definitely threw us through a couple loops here with the screen, and then that one resistor that we had to replace. So this has probably been so far the most difficult M1 board repair I've gotten so far as of this date. So as of, what date is it? December 7th. Our success rate on M1 boards has been 100% so far. That's destined to change, and I probably just jinxed myself. But so far, what I've seen on the original M1 boards, the 820 2016 and 820 2020, those two boards are pretty well designed, and we haven't seen any, they've been very fixable, I should say. Everything on the boards are kind of well compartmentalized on where all the components are, and they seem like they're designed pretty well. Now, the M1 Pro and M1 Max boards, I've seen one of those so far, and it's kind of not very much of the same, and I don't like them yet. So we'll have to see if they stand the test of time, but anyway, let's get this tested and let's see what happens. Alright, got everything plugged in. Let's just get our battery. That's the last thing. Cut it out because I know you guys don't want to see me struggle with connectors. And, of course, our screen connector just popped out. So, of course. That's one thing on this 820-2016 board is it likes to pop out because it sits in the enclosure kind of funny. So if you put any pressure on the board, your screen connector will pop up. So let's press that back down in there. Let's try not to disturb it. That's why it has a bracket on it. And the board doesn't have any screws, so it wants to slide forward a little bit, and that can complicate it. So just put pressure on it. I don't want the board to move around. Let's make sure our amp meter is live, and it is. And hopefully, hey, we already have an Apple logo. Look at that. Full backlight. So remember before it looked all nasty. I'll show you guys what I did. I'll be having a separate video up on FlexGate, and this was repaired in the same way. Spliced the cable. The original cable was kind of burned into it, and I could have fixed it by running a wire, but I don't really trust a flex cable that I've ran a wire to. But this is fixed. Look at that. Okay, M1 device saved. Power's on. Beautiful image on the screen. No liquid damage on the screen. And I'll call this one a success. So let's just go over what I did on the screen. You guys saw what I did on the board. On the screen, what we did is let's unplug our battery. I don't want to cause the backlight fuse to blow. There's a little bit of flux down here, residual liquid. You can actually see the bottom of the cable right here. Okay, cool. You can actually see the bottom of the cable. That's awesome. So what I did here is spliced a new cable in. This is the ugly side. This isn't the pretty side. All right. So what I did is I cut the cable about right here or so. Okay, cable was cut, and I soldered a new one on it, and it should be good to go. So you can see the little lip right there. That should be totally fine. I don't worry about longevity with these things. They're pretty sturdy, and in this particular instance, it's not really going to move a great deal. You know, it should be totally fine. It's not this isn't a concern for flexation issues, not like on the FlexGate, not on this machine. And then of course we have a brand new connector soldered in. A couple of NCs got burned, but definitely an improvement from how this looked before. So with that being said, this is done, and I hope this video helps you solve your problem. A lot of people, when they see screens corroded like that, they just throw it out. You know, it keeps something out of the landfill. One thing we do here, we have a collection of broken screens. We don't throw these things away. We don't recycle them. What we do is we save them for a rainy day when we need a connector off of them. And it's a great way, you know, a connector, flex cable, whatever, and it's a great way to take something that would normally go in the landfill to save something else that would also have went in the landfill. So it's kind of a nice touch. But anyway, thank you for watching. Hope this video helps you in some way.